Let's begin the last part of this tutorial. In this part, I will first discuss selecting the right compression approach in practice. For example, I will discuss how different performance criteria affect choosing a corresponding compression approach. I will also revisit the variational inference perspective on neural compression. And finally, I will go over some of the existing code repositories and other resources and discuss a few major research topics for future research. Let's discuss the criteria for selecting a compression model, beginning with lossless compression. First, we should be aware of our compression goal. Do we care about fast encoding and decoding primarily, or about compression rates? If speed is the most important, we might decide on conventional codecs or on probabilistic circuits, because these methods are at least an order of magnitude faster than current deep learning-based alternatives. And in fact, there's a concurrent tutorial on probabilistic circuits here also at NeurIPS. A slightly slower alternative are variational autoencoders and normalizing flows. These models are typically combined with bit-spec coding. If we only care about the best possible rates, we'll typically need to tolerate slower algorithms. For example, the best reported bit rates have been obtained by autoregressive models and diffusion-based models. Both decoding algorithms are inherently sequential and therefore slow. Another important decision depends on whether we want to compress individual data points or the data set as a whole. For example, we learned that bit-spec coding with chaining allows us to transmit site information along with the data, but this advantage only plays out if we have more than one data sample to communicate. If the data ordering does not matter, it turns out that we can actually achieve additional savings. The final design decision affects the type of entropy coder that we use. So here we have two options. Arithmetic coders lend themselves naturally to autoregressive modeling. And this also applies to probabilistic circuits and video compression models. And on the other hand, we have ANS coding. And this type of entropy coder is popular for most other neural compression approaches that don't have an autoregressive element. Let's talk about lossy compression. Here, our compression goals raise slightly different questions. Are we purely aiming for rate distortion performance, or do we also care about perceptual quality? In the first case, we will typically use a hierarchical variational autoencoder architecture. And for enhancing the perceptual quality, we can add an adversarial loss term to it by, in other words, augmenting the VAE with a GAN discriminator. We can also use diffusion models as our decoders. Another consideration is the encoding budget. For example, streaming services usually compress videos only once and don't care very much about this. In such situations, we can afford to spend a lot of compute to iteratively optimize our latent representations. And in other cases, the decoding budget plays a critical factor. If we have a high decoding budget, we can afford to use highly expressive entropy models, such as an autoregressive prior, but we can also afford potentially expensive decoders, such as diffusion models. If the budget is low, we need to work with simpler decoders, such as factorized entropy models that can be easily parallelized, or possibly a decoder based on a sparsified neural network, so that the reconstructions takes fewer flops. A final decision to make is whether we want to use stochastic reconstructions. And in this case, compression without quantization can be more efficient in terms of the rate distortion perception trade-off than existing approaches based on quantization. I want to spend a few words on the variational inference perspective on both lossless and lossy compression. In this tutorial, we encountered the evidence lower bound, or ELBO, and this objective appeared in two separate contexts. First, it appeared as an objective bounding the data entropy, and in other words, which is the lowest possible coding costs in lossless compression. And we learned that we can realize the coding cost given by the ELBO by compressing the data x using the likelihood, p of x given z, and compressing z using the prior. And since there can be multiple z's in practice that are compatible with x, we can get additional bits back by using a pseudo-random procedure to draw z from the stochastic decoder. The second meaning arises in lossy compression. Here we interpret the ELBO as a rate distortion objective. We can interpret the data log likelihood as a distortion metric and the KL term as the bit rate cost of compressing the latent representation. I want to discuss a few popular code repositories for neural compression. The TensorFlow compression repository implements several standard neural compression models for lossy compression, and it also provides a high-level API that can be used to build your own compression model. There's also an interactive Colab tutorial to help you get started. I would also like to point out the Compress AI project. This repository provides many of the same functionalities as TensorFlow compression, but in PyTorch. Also, Meta's neural compression repository builds on top of the Compress AI library using PyTorch Lightning wrappers, and its focus is mainly on lossless compression and contains JAX-based entropy coders. It also has bit-spec coding examples for diffusion models and sets. As an educational resource, we would like to point out our recent review article. And this article addresses the machine learning audience and covers the topics of this tutorial in greater depth. It also contains references to other more specialized review articles, for example, on video coding. Finally, we are working on creating a website for the community where we collect useful resources on the topic. And this website is currently under construction, so stay tuned. I want to spend the last few minutes talking about open problems for future research. By now, hopefully, I've convinced you that neural compression has great potential to drastically reduce the cost of information storage and transmission in many applications. But there are also many open problems and challenges along the way. One big roadblock is computational complexity. All methods are trained and evaluated on GPUs and assume essentially unlimited compute budget. But in the real world, for example, streaming on mobile, usually we have requirements on latency and power consumption and so on. In other words, at a much lower computational budget. So neural methods need to meet these demands and still deliver significant gains over traditional codecs in order to be widely adopted. Another concern in neural lossy compression is the risk of misrepresenting the original data in ways that traditional codecs cannot. And this is especially pronounced in the low bitrate regime, where the compression model can hallucinate many low-level details in the reconstruction to make it appear more realistic. In the case of image compression, say of a human face, this can result in the identity of the person being misrepresented, raising questions about fairness and trustworthiness. And in fact, this phenomenon can occur even without targeting realism. For example, as we reduce the bitrate, reconstructions from a variational autoencoder trained on mean squared error distortion become increasingly more similar to the average of the training set. A related issue is the lack of control over stochastically generated reconstructions, so that different reconstructions are seen over time or by different users. And so this furthermore adds to the risk of miscommunication. Conditioning the generative reconstructions on semantic labels could be a solution, and the recent success of text-to-image models may open up new possibilities with this approach. Another challenge, as with other applications of machine learning, is to prevent catastrophic failure of neural compression models on out-of-distribution input and adversarial examples. And we saw that quantization required various approximations for end-to-end training, and that compression without quantization allowed us to avoid this issue. But more research into efficient implementation is needed to make this approach more practical. And finally, we still need a better theoretical understanding of various aspects of neural compression, such as its theoretical performance limit and optimality conditions. To conclude, we talked about neural compression, a field at the intersection of machine learning and information theory that tries to learn codecs from empirical data. This approach is very flexible and can be applied to many different types of data. In lossless compression, this is really just generative modeling as its core, where we estimate the best probability density of the data and then hope that entropy coding takes care of the rest. But it also requires art and engineering to design models and entropy coding algorithms that actually ensure a practical compression method. The trade-off here is mostly between bitrate and computational efficiency. Lossy compression can be thought of as representation learning with an entropy bottleneck. So besides the bitrate, we also care about other aspects of the compressed representation, such as distortion, the perceptual quality, the relevance for downstream tasks, and so on. So the objective really depends on the application. Also, computational efficiency is crucial for a wider adoption of these methods. Neural compression is overall inspired by many areas of machine learning and statistics, such as generative modeling, variational inference, information theory, computer vision, etc. But it also has its own and unique contributions to offer. For example, it will enable new types of media, it will make information processing more efficient, and it will also bring in new ideas and methods to the field of information theory. With this, we would like to thank our audience for their time and end our presentation, and we look forward to your questions.